Hello everyone. The next topic that we have to start is the steady state sinusoidal analysis. Now see, till now we have seen that all the currents and voltages that were appearing in the circuit, they were DC in nature. So a DC voltage or current, say this is time and this is some current, is like this. So every voltage and current that we came across till now was DC in nature, or a unidirectional voltage or current, as you may call it. When we go to the next topic, which is steady state sinusoidal analysis, the first thing that will happen is the voltages and currents that we shall now come across will be sinusoids in nature, sinusoids of some particular frequency. Is this okay? So say if one circuit is excited by a source of say 50 hertz, or two sources or three sources of some frequency, say 50 hertz, so all the currents and voltages that will be produced in that particular circuit will be having the frequency 50 hertz. Like we have calculated voltages at different points, current through different branches in the circuit, they all were DC in nature. Now all those currents will be pure sinusoids of some particular frequency. All the sources that we shall have connected will be having the same frequency from now onwards. Although we will also solve the problems where the circuits will be excited with multiple frequency sources, like one source is 50 hertz and other is 60 hertz, then what will happen, we will have to go to the superposition theorem for that. But for the time being, when we are studying steady state sinusoidal analysis, one thing we must understand, all the voltage sources and current sources that will appear in the circuit will be of same frequency in the beginning. Later on, we shall change the frequency of different sources and see how the analysis goes forward. Alright, so let us first understand the basics of the sinusoidal analysis. See, we have this word steady state coming here. We have the word steady state. Now say we have a sinusoidal voltage source and it is to be switched across this series RL combination. So this is Vs is equal to Vm sine omega t. Alright, and this is some current I. Now what happens when you close this switch? This current takes some amount of time to reach its steady state. This you must have studied in your control system course, that when we close the switch at t equal to 0, it will take 4 time constants, 4 upon zeta omega n, that is 4 time constants, for this current to come to a steady state. Once this current comes to a steady state, then this current will be a pure sinusoid. So what is the meaning of the steady state? That all the transients in the system have died out. All the transients have simply gone, and we have to analyze this circuit once 4 time constants have passed, and then the analysis will start. Alright, so what we are doing is we are assuming this switch closed, and after closing the switch, system coming to a steady state, and then we are starting the analysis. That's why the word steady state sinusoidal analysis. Alright, so let us first go through some of the basics which we must know before starting the numerical problems. Now what are the basics? We have to first get familiar with the circuit elements which shall be there. We shall come across mainly these three circuit elements. So we have a resistance, we have inductance, and we have capacitance. The voltage here is VR, the voltage here is VL, the voltage here is VC. The current is IR, current is IL, and the current is IC. Alright, so as you know, these three are circuit elements only. Some basic equations which you are already familiar with. Let us first go through those equations. We are going to come across these three basic circuit elements. This resistance is having a relation VR is the current into the resistance R. Alright, so this is the relation for a resistance. Voltage across the resistance is current through it into R. Alright, now if we look at this, the ratio of the voltage across an inductance divided by current flowing through an inductance is called as the inductive reactance. We call it as inductive reactance, which is equal to omega L, having the dimension of ohms. Is this okay? So the magnitude, I will call it magnitude of VL by IL, it is in magnitude omega L, where this omega is 2 pi f, this much of radians per second, this omega, whereas this f is in hertz and this is in radians per second. Alright, similarly the ratio VC by IC magnitude, we call it as XC, and this becomes 1 upon omega C, which is again having a dimensions of ohms. Here it will be measured in Henry, MKS units, it will be measured in farad. So this is ohms. I think you are familiar with these relations already. Now, by the very nature of the inductor and capacitor, the voltages and currents, they have a lag angle of 90 degree or lead angle of 90 degree. We generally look at the angle of current with respect to voltage. When we see the angle of current with respect to voltage, it is lagging in case of an inductor and it is leading in case of a capacitor. Why? Because we have the general relations BL is L di by dt. This is the relation. Alright. Or the current through an inductor is 1 by L integration of VL dt. So if this becomes a sine term, this becomes a cosine term, because differentiation of sine is a cosine. So if I is sine omega t, it will be corresponding to cos omega t, and sine omega t and cos omega t, they already have a 90 degree phase shift among them. Similarly for a capacitor, you see IC is C dV by dt. C dV by dt. Again, if one corresponds to sine omega t, other will correspond to cos omega t. So sine omega t, cos omega t will have the 90 degree phase shift between them. So in case of an inductor, the current lags with respect to voltage by 90 degree. In case of capacitor, the current leads the voltage by 90 degree. This you are already familiar with. Alright, so this we shall further take up. Now, before taking our discussion further, I would like you to understand some basic concepts of phasor algebra or the phasor calculations, how the phasor calculations are done. Because please understand, since every quantity is a sinusoid, they will have some phase difference among them. one will lead the other by some degree, one will lag the other by some degree. So not only the quantities will have magnitudes, but they will have their individual phases. Like one angle 30 degree amperes, I think you are familiar with this. 2 angle minus 60 degree volts. So not only the magnitude but the angle needs also to be defined. Since there are many sinusoids, 2 voltages, 3 currents, there are 5 sinusoids. One of the sinusoid is taken as the reference, which you call as a reference phasor, and with respect to the reference phasor all the other phases are measured. So we have to first go through this process as to how phasor algebra comes into the picture, and in the process we shall also see the operator J. How does the operator J comes into picture? Now see, representation of a phasor. How can we represent a phasor in different ways? As I said, every phasor have some angle and some magnitude. Alright, so if you have some current, say 20 angle minus 30 degrees amperes, something like this. This means what? This means that the magnitude of the current is 20 amperes and it is the RMS value of the current. In the sinusoids, when we specify the voltages and currents, when you say 240 volt is the domestic supply, this 240 volts is the RMS value. Similarly, when you write something like this is an RMS value, and this is called as its phase. This is the magnitude, this is the phase. Minus 30 degree means the current lags the reference phasor. Whatever might be the reference phasor, it has to be chosen. Like we have to choose a reference node while we are doing the DC analysis or this AC analysis. So reference node has to be chosen always, but in sinusoidal analysis you must know where does your reference lie, but you must know what is the reference phasor. These two things have to be defined. The reference node, which is to be defined always whether AC or DC analysis, and in AC analysis we must always specify what is the reference phasor, and with respect to that reference phasor we indicate all the other phasors. So this is the general representation that we choose, and it is called as the polar form of phasor representation. This is called as the polar form of phasor representation. Is this okay? This can be written as 20 cos 30 degrees minus j sine 30 degrees. So this is 20 into 1 by 2, this is root 3 by 2, so 20 root 3 by 2 minus j 10, this much of amperes. Sine 30 is 1 by 2, so it becomes this much. Hence we call it as the rectangular form or Cartesian form, as you want to call it, Cartesian representation. Is it okay? So on the complex plane, this is the real axis and this is the imaginary axis. This is the real part of I, this is imaginary part of I. So if you see the real part, this is 20 root 3 by 2 and this amounts to 10 root 3 basically. So this is 10 root 3. So 10 root 3 is going to be, say, somewhere here. This is 10 root 3 and this is 10. So when you see this angle is theta and this magnitude is 20 ampere. Right, whereas this theta is tan inverse the real part upon the imaginary part upon the real part. So tan inverse 10 upon 10 root 3, so it is equal to 30 degrees. So this is the phasor. This 20 ampere phasor is having an angle of 30 degrees, or here, since this is minus, this imaginary part is negative, so it will be minus 30 degrees. So if it is plus 30, this is plus, then minus 30 will be downwards, so minus 30 will come out here. So if it was a plus, suppose it was a plus and plus, then it will be theta on the positive side. So this is theta. If this is theta plus, then this is theta plus. If it was minus, then this would be minus 30 degree. So if we are measuring it in the anti-clockwise direction, theta plus is 30 degrees, and if we measure it clockwise, it is taken as with the minus sign, so it becomes minus 30 degrees. So this is called as rectangular or Cartesian form. It can be represented on the complex plane like this. You are already familiar with. Another way of representing it is, we can call it as I phasor is 20 e raised to power j pi by 6, this much of amperes, and that is called as the exponential way of representing a phasor. So either we can choose the polar form, or we can choose the Cartesian form, or we can choose the exponential form. Without the loss of any generality in the problems to come, we shall always prefer this particular form of representation, because this gives us a clear information as to what is the magnitude and what is the phase. How much is the magnitude of the current, and by what angle will it lag or lead the reference phasor. So polar form, Cartesian form, exponential form, we have to deal with these forms of phasors. When I say phasor, I mean to say a voltage or a current primarily, although even the power can also be complex, which we shall see. Complex power is P plus jq, the active power plus j times reactive power. So when I say phasor, for the time being, let us understand it as either the voltage or the current, although power can also be complex, which will come at the later stages. Alright, so these are the ways of representing a phasor which we shall take up. Now see, if we want to represent various sinusoids which are lagging or leading each other by some angle, representing the sinusoids by the sine waveform might be a complicated phenomenon, because if you have 5 sinusoids, say something like this, another sinusoid is this, another sinusoid is this, you see there are 3 sinusoids, voltage or current, with respect to this axis, omega t axis. Alright, then omega t is that angle theta only that we just saw. So omega t, this is in radian per seconds, this is seconds, so in totality it is a radian. So radian is the angle that we measure with in the anti-clockwise direction, positive, and if it is clockwise, then it is negative. We shall also see why it is positive in the anti-clockwise direction and negative in the clockwise direction. Now when you see this, there are 3 phasors, but it is very difficult to understand and comprehend who is lagging by what angle with respect to a phasor and who is leading by what angle with respect to another phasor. As the number of waveforms increase, this further gets more and more complicated. So for this case, what we have to do is we have to take a phasor diagram approach. When we have to take the phasor diagram approach, we represent the sinusoids by the phasors. Now why do we represent sinusoids by the phasors? Let us understand this. Alright, so we shall now see that how can we represent a sinusoid by an anti-clockwise rotating phasor. So we have a circle which is a 360-degree curve, and we have this phasor. Say this is the center O and this is say point A. Now what we shall do is, as this phasor rotates, its vertical height, or should I say its vertical projection, will increase with respect to this reference, which is the 0 axis. Right now this phasor is in position OA. If it is in position OA, the vertical height of this A from this reference is 0. So I am having a projection at 0. As this phasor rotates anticlockwise by an angle 30 degrees, as you can see, each division is 30 degrees, right? So these are 12 different parts of the circle. So 12 parts, each part is 30 degrees, so it becomes 360 degree. So every part is 30 degree. The moment it rotates anticlockwise by 30 degree, its vertical projection will reach at this point. Say this point is B. This point is B. So its projection, it reaches here. Let me call it B dash. Similarly, this point is C. Its vertical projection is C dash. So this is the vertical projection of the phasor. This is say point D, so that this point becomes D dash. Alright, and then we can continue this exercise further. This is the projection of A, let me call it A dash. Alright, so as this phasor is rotating anti-clockwise, its vertical projection is following a sine law. This you can see. If you see this height, this is 0 height, then it increases, then it increases, then it further increases, then reduces, becomes 0, increases in the negative side, and this is how the sine law is followed. It means when the phasor is rotating anti-clockwise, its vertical projection is following a sine law. So you can join these points by a smooth curve, and you can then say that it is a perfect sinusoid. So what is happening is, as the phasor is rotating anti-clockwise, the vertical projection is following the sine law. If you see at position B, this is the vertical height from, say this is point O, this is everywhere point O. So from OB dash, this OB dash is the instantaneous value of this phasor, because this is the vertical height. So at position O, this is the value, so we call it as, this value is at this instant, so we call it as instantaneous value. Alright, so if this is height say Vm, this is height say Vm, then this OB dash is, you can see this angle is 30 degrees, this is 30 degrees. So this height from O to B dash will be, if this is Vm, this is Vm sine 30 degrees. Vm sine 30 degrees. Similarly, this C point is at Vm sine 60 degrees. This is Vm sine 90 degrees. This is Vm sine 120 degrees. This is Vm sine 150 degrees, and this is Vm sine 180 degrees. Moving forward, this is Vm sine 210. This is Vm sine 240. This is Vm sine 270. This is Vm sine 300. This is Vm sine 330. This is Vm sine 360. So this vertical height is this height, which is nothing but the vertical projection of the phasor. See, it's like this. If you have this as your reference, and this is say angle 30 degrees, this height is say some height Vm, then this height must be Vm sine 30 degrees. So it is the vertical height Vm sine 30 degrees. So this Vm has a vertical projection. Similarly here we have, say this is Vm, so this has to be Vm sine 30 degrees. So vertical projection of a phasor gives its instantaneous value. It's a very important statement, and it is very useful for electrical engineering students when they go to the electrical machines, induction machines, and MMF waveforms and other. When they draw, it is very important, this statement, that the vertical projection of a phasor is its instantaneous value. Horizontal projection doesn't make any sense. This is horizontal projection, Vm cos 30 degree. It's of no use to us. But vertical projection is always the instantaneous value of the phasor. We call the rotating phasor as anti-clockwise rotating phasor, and this is the reason why anti-clockwise direction is called as the positive direction of rotation. Is this okay? So it is always convenient to represent the phasors by phasor diagrams. So if you have something like this, now these are 5 phasors. Instead of drawing 5 sine waveforms, it is always convenient to have 5 phasors like this with the respective phase differences among them. One of the phasors is to be taken as the reference phasor. So this is, say, some voltage which is having value 100 angle 0 degree volts, and with respect to this we measure other phasors I1, V2, I2, I3 and so on. This angle in the positive direction, means in the anti-clockwise direction, is measured as positive, whereas if it is measured like this, it is measured as negative. So instead of drawing 5 sine waveforms, it is better that we use the phasor diagram. So this phasor diagram approach we are going to use during the analysis of sinusoidal circuits. Those who are EE students, it will be further useful to them when they study electrical machines and draw the phasor diagrams of transformers, induction motors, and others. Even in the power systems, when you have to draw the phasor diagrams of transmission lines, so drawing the phasor diagram for the further analysis, it makes things easier there. So we must understand the very basics of phasor diagrams comes from the network theory, and this is how a sinusoid relates to an anti-clockwise rotating phasor. Is this okay? This discussion can be taken further in case of the resistance, inductance and capacitance. So let me again redraw the 3 elements. So this is your resistance, inductance, capacitance. This is voltage VR, this is voltage VL, and this is voltage VC. Alright, so these are the 3 circuit elements that we will come across. We can also indicate the currents. This is IR, this is IL, and this is IC. Alright, it is a general practice that we do not show the polarity of voltages because it is a sinusoid. It is already changing its polarity at the supply frequency. Say if it is a 50 Hertz waveform, then there are 50 positive cycles and 50 negative cycles. So the polarities are anyway changing at the supply frequency. So we generally choose not to indicate the polarities. Although polarities are indicated when there is a special case that we shall see while solving the numerical problems, but we shall maintain this practice that we will not show the polarity so long as it is very necessary. It is not very necessary to represent it. We will not represent it. The voltages will be written without any polarity. Is this okay? Now you are all aware of this. Here VR and IR, if this is VR, then IR will be in phase with this. Alright, so if you have theta is equal to omega t, here omega is in radians per second. What is omega? It is the angular velocity with which the phasor is rotating. Alright, which is always in radians per second, and t is in second. So radian per second into second becomes radian. So this theta is usually measured in radians and can be converted to degrees whenever needed. Alright, so here if this is your waveform of voltage, then if this is your VR, then this is IR. Alright, so VR and IR are in phase, and you know if VR phasor and IR phasors are there, let me call it some VR magnitude angle 0 degrees, so that this IR will also be having the same phase. For a resistance, VR and IR, they are always in phase, and the ratio is simply VR phasor upon IR phasor, which is anyway VR magnitude upon IR magnitude. I think this we already know for a resistance. Voltage and current, voltage across the element, current through the element, they are always in the same phase in case of a resistance. If it is an inductance, then we have this as VL and we will have this as IL. If you see this angle is minus 90 degrees. Since we are measuring it clockwise, the current is having an angle minus 90 degree with respect to voltage for an inductor. So what happens here? If you have the inductor voltage like this, say this is VL, then inductor current will lag by 90 degrees. So lagging by 90 degrees will shift the waveform towards right by 90 degrees. So you will have this as the waveform of IL, and this can be further extended like this. So this angle, if you see, is 90 degrees or pi by 2. This is theta is equal to omega t. So this is 90 degree or pi by 2 radians. Is this okay? So what happens here is, if VL is your reference phasor, then VL is some magnitude VL angle 0 and IL is some magnitude IL angle minus 90 degrees. Is this okay? So the inductive reactance XL, when you divide a phasor by a phasor, you will definitely get the phasor. So it is VL phasor upon IL phasor. So it will be VL magnitude upon IL magnitude. Let me write it in capital. And this is angle 0 and this is angle minus 90 degrees. So when you divide two phasors, the phase of the denominator get subtracted from the phase of the numerator. So VL by IL is XL, and this becomes XL angle 90 degrees. So that's why this becomes J XL, this much of ohms. So in phasor terms, the parameter J, or the operator as you may call it, the operator J will be there This operator j is analogous to that number iota that you had studied there, but here it becomes an operator. This operator j has a numerical value 1 angle 90 degrees. Alright, so this is analogous to that number iota only, but when you multiply any phasor by j, that phasor gets rotated by 90 degree in the anti-clockwise direction, because the magnitudes will get multiplied, the phase they get added when you multiply. When you divide, as you all know, the phase of the denominator get subtracted from the phase of the numerator. So j is 1 angle 90 degree, it is an operator. So with an inductive reactance, always we have this j. Alright, if we talk about the capacitance, alright, say this is your capacitance. The current through the capacitor is say IC, the voltage across it is say VC. Alright, so here the current will lead the voltage by 90 degrees. This is your IC. So the current would lead the voltage by 90 degrees. Means if voltage is your reference, so the current has to lead this is say VL, this is theta is equal to omega t. So if it has to lead, it should lead by 90 degrees. So it will lead by 90 degrees, and this is angle 90 degrees or pi by 2. This blue is the current, sorry, this is VC. So this has to be IC. Alright, so the current is leading the voltage by 90 degrees. So if you take VC as a phasor, which is VC angle 0 degrees, and IC you take it as a phasor as IC some magnitude angle plus 90 degrees. So the inductive reactance XC, which is VC phasor upon IC phasor, so it becomes VC angle 0 upon IC, these are magnitudes, angle 90 degrees. So VC by IC becomes what? XC, the capacitive reactance. So XC angle minus 90 degrees, or you can call it as minus JXC. So this is the reason why we would always write minus J with the capacitive reactance in order to accommodate the phase of voltage with respect to current, because the current flowing through a capacitance must lead the capacitance voltage by 90 degree, so it gets accommodated by this minus J. And for an inductor, the current must lag the inductor voltage by 90 degrees, so that gets accommodated if we write it with J. So this practice we always maintain, you are familiar with this. Whenever we write a capacitance or inductance, so we write it as J5 ohms. This is because of this reason. And when we write as capacitance, it is written as minus J2 ohms. So we maintain this practice whenever we have to deal with the problems of the sinusoidal circuits. Inductive reactance with plus J, capacitive reactance with minus J, and there is nothing on the resistance because there is no factor of J as such, there is no angle of lagging or leading as such. So resistance is simply written as a number. So if it is a resistance, it is simply written as say 5 ohms. Alright, so these are some of the basics which we must understand before we start solving the problems of network theory. Alright, so we have seen the basics of the phasor algebra. Let us move forward to the numerical problem solving, where we shall apply these basics to calculate further things in the circuit. Now let me take a very simple example to start with. Say we have a series RL circuit. Say this is your supply voltage, which we shall take as the reference, and this is 100 angle 0 degree volts. This is the current IS. The S subscript here represents the source voltage and the source current. This is, say, a resistance of 3 ohms, and this is, say, 0.04 Henry. Alright, say the angular frequency of this source is 100 radians per second. Is this okay? So once you have omega known to you, you can calculate the inductive reactances or maybe the capacitive reactances whenever needed for the circuit. Now omega is 100 and L is 0.04 Henries. So omega L becomes 4 ohms. 100 into 0.04 becomes 4, and we shall write it as J4 ohms. J4 ohms, right? So 0.04 Henry can be replaced by J4 ohms in the circuit. Now what are the phasors that we shall indicate? This is VR, voltage across the resistance, voltage across the inductance, the source current, the source voltage. Alright, so source voltage, source current, resistance voltage, resistance current, these four are the phasors that we shall calculate, and with the help of these phasors we shall calculate very many things for this numerical. Now how the calculation proceed? What are all the possibilities that we can take for this particular circuit? Now see, first of all, if you see the impedance Z, this is the total impedance. Total impedance is a complex number 3 plus J4 ohms. So Z is 3 plus J4 ohms. Equivalently, we can represent it as 5 angle 53.13 degrees, this much of ohms. Tan inverse 4 by 3 is 53.13 degrees, and under the root 3 square plus 4 square is 5. So the magnitude is 5. I can get the current phasor once I divide the voltage phasor by the impedance phasor. Is this okay? So voltage phasor is 100 angle 0 degrees and impedance phasor is 5 angle 53.13 degrees. Alright, so this becomes 20 angle minus 53.13 degrees amperes. Alright, so this is the current phasor having a magnitude this, and it is lagging the supply voltage by 53.13 degrees. This also gives you the information about the power factor at the supply. This is Vs, which is 100 angle 0 degrees volts, and this is Is, which is 20 angle minus 53.13 degrees amperes. So this angle is 53.13 if we only look at the magnitude. So 53.13 is the magnitude of this angle, and since the current is lagging the voltage, we take this as a minus sign. So this is generally we call it as the power factor angle. This is power factor angle, and cosine of this angle is what you call as the power factor. So cos of this angle power factor is cos of minus 53.13 degrees, and it comes out to be 0.6 lagging. The supply power factor for an RL circuit has to be lagging because the current will lag the supply voltage by some angle. That's why this is lagging power factor. Since cos of minus theta is also cos theta, we have to specify always with the power factor whether it is lagging or leading. Even if this was plus 53.13, it would have been 0.6 only, but then we would have written leading in the bracket of the power factor. Is this okay? So whenever you are specifying the power factor, we must always specify whether lagging or leading. Is this okay? Now what are the further calculations that we can do? See, if Vs is to be represented as a function of time or as a function of omega t, how would we represent it? What is the value? 100. 100 is the RMS value. So 100 root 2 sine omega t, omega is also 100, so sine 100 t volts. This is your Vs phasor or Vs as a function of omega t. If you want to write Is here, so Is will be 20 is the RMS value, root 2 sine 100 t minus 53.13 degrees, this much of amperes. Is this okay? So the supply voltage is 100 root 2 sine of 100 t, and the supply current is this. Alright, this is how we can represent voltages and currents as a function of time. Is this okay? Now we can do the further calculations. We can calculate VR phasor as IS phasor. जैसा आप देख सकते हैं कि ये एक सीरीज सर्किट है. अगर ये एक सीरीज सर्किट है तो द करंट बीइंग द सेम, whatever is the supply current is the resistance current is the inductance current. So we have same current flowing through the entire circuit. All right, so Is into R, right? So we put this Is as it is here, so it becomes what? It becomes 20 angle minus 53.13 into the resistance is 3 ohms, so it becomes 60 angle minus 53.13 degrees. So VR as a function of time can be written as 60 root 2 sine 100t minus 53.13 degrees, this much of volts. Is this okay? Now we can calculate VL. So what is VL? VL is Is phasor into JXL. This is what? This is XL phasor. XL phasor is JXL. Here XL is a number, right? Which is XL is 4 ohms. So we always write it with a J. You know the reason why. So we shall write it as 20 angle minus 53.13 degrees into J4. Now what is J4? J4 is 4 angle 90 degrees. What is this basically? This is 4 angle 90 degrees ohms. Alright, so it comes out to be 80 angle. When you add this 90 degree and this minus 53.13, you get what? You get 36.87 degrees, this much of volts. So as you can see, this phasor VR is in phase with Is. Why? Because for a resistance, this voltage and this current have to be in phase. Alright. Minus 53.13 degrees and plus 36.87 degrees is a total displacement of 90 degrees. So this current must lag this voltage by 90 degree by the property of the inductor. Is this okay? So we can write this VL as a function of time as VL is equal to 80 root 2 sine of 100t plus 36.87 degrees volts. Alright, तो ये जो वोल्टेज है VL, ये एज अ फंक्शन ऑफ टाइम हम इस तरीके से लिख सकते हैं, ओमेगा इज 100 रेडियंस पर सेकेंड. Is this okay? So we have calculated Is, VR, VL, and we have also written them as a function of time. Is this okay? Now we can also represent everything on a phasor diagram. How can we represent it? See, this is your reference phasor Vs. Vs, as you can see, is a phasor sum of VR and VL. So if we have VR and VL as the two sides of a parallelogram, the diagonal will be the resultant, and that will be Vs. Why? Because Vs is the resultant of VR and VL. So you can see, if this is your Vs, your VR should lag by 53.13 degrees. So let me draw it like this, and VL should lead by 36.87 degrees. So this will be VL phasor. This is VR phasor. Is this okay? So we can make it a complete parallelogram like this. Say you have to draw a line parallel to this. So this should go up to this point, and this should be parallel to this, so that this is VR, this is VL, and this is your Vs. So what is Vs? This is 100 angle 0 degree volts. Alright, this angle is minus 53.13 degrees. This angle is 36.87 degrees, and you can clearly observe this entire angle is 90 degrees. IS का एंगल अगर आप देखें तो IS का एंगल भी वैसा ही है जैसा रेजिस्टेंस के वोल्टेज का है, क्योंकि एक रेजिस्टेंस के लिए द इंडक्टेंस, द वोल्टेज एंड द करंट, दे आर इन फेज ऑलवेज. सो इफ दिस इज VR, this has to be IS only. Here this is IS. The length of VR, comparatively we have to make it a little smaller compared to VL, क्योंकि VL की लेंथ हमें ज्यादा बनानी है, क्योंकि VL का मैग्नीट्यूड ज्यादा है 80, whereas VR का मैग्नीट्यूड is 60. So VR is relatively small when compared to VL. Is this okay? So this is 100 angle 0 degree volts. This is VR. This is VL. Is this okay? So this you can call it as a phasor diagram. This entire phasor diagram is rotating at omega is equal to 100 radians per second. This entire you can consider it to be the center of rotation, and then this is rotating at the constant frequency omega is equal to 100 radians per second. So this is the phasor diagram. Is this okay? So we have to follow this particular approach for representing the phasors, and then representing them on a neat and clean phasor diagram like this. Alright, so We can take these results further and we can do further calculations. Let us go to the power calculations now. So the results that we have is, we have Vs, which is already given, 100 angle 0 degrees, volts, Is as 20 angle minus 53.13 degrees amperes. Alright, VL is 80 angle 36.87 degrees, and you can see the phasor diagram. If you see VL with respect to IS, VL is leading by 90 degree, you can see in the phasor diagram, and in case of a resistor, VR and IS, they are in phase. So you can see this angle is 90 degree, this is 36.87 leading with respect to reference, this is minus 53.13 lagging with respect to reference, so this sums up to 90 degrees. And VR, as we calculated, was 60 angle minus 53.13. So these angle must be the same because they are to be in phase, the resistance voltage and the resistance current. Alright, now see, we can now calculate the active and reactive power supplied by the source to this RL circuit. Alright, those who are EE students, they know that the reactive power is to be taken positive for an inductor, because an inductor is a sink of reactive power, it absorbs reactive power. Whereas for a capacitor, the reactive power has to be taken negative, because a capacitor is a source of reactive power, it is a source of lagging VARs, whereas an inductor, it absorbs the lagging VARs. Is this okay? So these are the results that we got. Now how can we do the power calculations? Now see, this resistance will always absorb active power. So how can we calculate the active power absorbed by the resistance? One way of calculating it is, which we did in the DC analysis also, it is simply like this: 20 square into 3, that is 1200 watts. We generally denote it by P. Alright, this is one way of calculating the active power. This can also be calculated as the RMS value of the voltage, supply voltage, the RMS value of the supply current, and cos of the angle between them. What is this theta s? This theta s is the angle of current that it makes with the voltage, although we have to take only the magnitude of this theta s here, because we are calculating the magnitude of P. Alright, so this is 100, this is 20 cos of 53.13, and cos of 53.13 is again 0.6. So this comes out to be again 1200 watts. Is this okay? Third way of calculating it is P is equal to the voltage appearing across the resistance squared by R. This is third way of calculating the power absorbed by a resistance. So in our case, VR is 60 squared divided by 3. So it again amounts to 1200 watts. Is this okay? This is how we calculate the active power. Is this okay? This active power is supplied by the source to this circuit, or we can say to this resistance, because in this circuit only this resistive element will absorb the watts. or it will consume some wattage. The dissipation is always in terms of watts. Is this okay? This inductor will absorb reactive power. I will have a detailed discussion on reactive power in the video to come, because some discussion on reactive power has to be done here, and it is all the more important for those who are EE students, because they have to deal with the reactive power in the electrical machines and in the power systems and the power electronics, which they would study as their core subjects. So reactive powers discussion will be there in the videos to come. Right now we are focusing on how the reactive power can be calculated for a given circuit. One thing, as I just told you, we must remember that an inductor is a sink of reactive power. It absorbs reactive power, and a capacitor is a source of reactive power. So we shall also have a look at this in the time to come, where we shall study the resonance and other topics. There also we shall relate these things. But we must remember that then an inductor absorbs reactive power and a capacitor is a source of reactive power. So how the reactive power calculations are done? Active power is calculated like this, right? How is the reactive power calculated? Again, it's very easy. The reactive power, which is represented generally by Q, reactive power is Is square XL in magnitude. Alright, so resistance is replaced by a reactive term. This is reactance, inductive reactance. So this becomes 20 square into 4. So it becomes 1600 VAR. We call it as volt ampere reactor. Although dimensionally active and reactive powers are the same, but just to differentiate between them, we express the active power in watts. So we have to, just to differentiate, we express the reactive power in VAR. So this is 1600 VAR. This much of reactive power is absorbed by the inductor, and therefore this is supplied by the source. हम लोगों ने पावर बैलेंस किया डीसी सर्किट्स में, वही पावर बैलेंस हम यहाँ भी कर सकते हैं, बट वी मस्ट अंडरस्टैंड हियर वी हैव टू बैलेंस P and Q both, right? Because whatever is the active and reactive power supplied by this source has to be taken by the circuit elements. This would absorb active power always, and this would absorb reactive power. A pure inductor or a pure capacitor will never absorb the real power or the active power. Active power is also called as real power. Why? Because dimensionally what was it? It was VI cos of angle between voltage and current. Angle between voltage and current for an inductor and for a capacitor, the magnitude is always 90 degree. So V into I into cos of 90 degree will anyway become 0. So a pure inductor will never absorb any active power, neither a capacitor, pure capacitor, will absorb any active power. Is this okay? So this is first way of calculating reactive power. We represent it by Q. Another way of representing calculating it is voltage magnitude, current magnitude, sine of theta s. This theta s is again 53.13, but as I told you, we only take the magnitude of it. Is this okay? So what is the voltage? It is 100. What is the current? It is 20. Sine of 53.13 degrees. Alright, so it comes out to be again 1600 VAR, because this is 0.8. So it comes out to be 1600 VAR. Third way of calculating the reactive power is voltage across the inductor squared divided by XL. So it is 80 squared upon 4, which again amounts to 1600 VAR. So it becomes 1600 VAR. This is how the reactive power is calculated. Another way which we can add both in the active and reactive power. One way of calculating the active power, which I did not mention earlier, voltage across the resistance into current through it. So voltage, what is the voltage across the resistance? Voltage across the resistance was 60, and what is the current through the resistance? 20. So it is 1200 watts. Q, it is the voltage across the inductance multiplied by the current flowing through the inductance. So it is 80 into 20 is equal to 1600 VAR. So there are four ways, 1, 2, 3 and 4, through which reactive power is calculated, and this active power, this and 3 that we saw previously, four ways in which active power can be calculated whenever needed. Please understand, when you say V square by R or V square by XL, we have to look at the voltage across that element. Don't take the source voltage while you are squaring and dividing it by reactance or resistance. When you say V square by R, it is, to be very specific, VR square by R. The voltage across the resistance squared by R is the power dissipation, which amounts to I square R. Is this okay? Similarly, voltage across the inductance squared divided by XL is the reactive power absorbed by the inductor. Is this okay? There is one more way in which you can calculate this power, complex power. It is by definition Vs phasor, Is phasor conjugate. Is it okay? Now the question comes, why do we take the conjugate of this? See, let me first tell you the calculation and then I will tell you why do we take the conjugate. We multiply these two phasors. So this is 100 angle 0 degrees and this is 20 angle minus 53.13 degrees, but conjugate. So when you take the conjugate, this angle turns plus, so 100 angle 0 degrees, 20 angle 53.13 degrees. So just to remove this asterisk, we are changing the phase, minus sign is converted into plus sign. So it becomes 2000 cos 53.13 plus j sin 53.13. So it becomes 0.8 and this becomes this becomes 0.6 and this becomes 0.8. So in totality it becomes 1200 plus j 1600, this much of volt ampere, and this is called as complex power absorbed by the RL circuit. Out of this is P, or active power measured in watts, this is reactive power measured in VAR. So this is in watts and this is in VAR. Is this okay? Now please understand, यहाँ पर एक प्रश्न आपके मन में आ सकता है कि हमने ये conjugate क्यों लिया? Why it is the definition of complex power V into I into conjugate, VI conjugate. Please understand, as I told you, an inductor is a sink of reactive power. If an inductor, which is the part of the load, even the inductance or the capacitance, we are taking it as a part of the load. So लोड का नेचर होता है कि वो पावर हमेशा एब्सॉर्ब करता है, राइट? An inductor absorbs reactive power, but a capacitor, which is although a part of the load, is a source of reactive power. So a capacitor, which is the part of the load, we have to make the reactive power negative for a capacitor. And an inductor, since it absorbs reactive power, which is what a load is supposed to do, it is supposed to absorb power. So why have we taken the conjugate is, If we did not take any conjugate, then there would be minus sign here. If this minus sign was there, this would have been a minus sign, then this would have been a minus sign. The reactive power would have become negative. So this would be against our convention of reactive power flow. An inductor is a sink of reactive power and a capacitor is a source of reactive power. Just to satisfy this statement mathematically, we must take this conjugate. This is the reason why we take this conjugate. So in one go we are able to calculate the active and reactive power. Alright, this brings us to three triangles. What are those three triangles? See, you must have heard of it. We have impedance. What is the impedance? 3 plus j4. So on the complex plane, if this is 3, this is 4, this is 5, right? So this is your R, this is XL, and this is Z. Of course, these are magnitudes. And this is your angle theta S. What is theta S? Theta S is tan inverse 4 by 3, which is 53.13 degrees. This is the impedance angle also. This is the power factor angle also. If we multiply these three phasors by I square, so when you multiply the resistance or impedance by I square, it becomes what? It becomes power. Or if you don't want to multiply it by I square, first let us multiply it by I. So it becomes IR, it becomes IXL. So IR becomes voltage of the resistance and it becomes voltage of the reactance. So when you multiply it by IS, multiplied by IS, what is IS magnitude? IS magnitude is 20 amperes. 20 amperes. So it again becomes a triangle like this, and so this has to be 60 volts, this has to be 80 volts, and this has to be 100 volts. The angle does not change क्योंकि हमने एक ही नंबर से तीनों साइड्स को मल्टीप्लाई किया है, तो एंगल चेंज नहीं होगा, because after all the ratios have not changed. If the ratios have not changed, trigonometric ratios, then the angle must not have changed. So this is VR, this is VR, this is VL, and this is VS. Is this okay? So you can further multiply this by current. If you further multiply this by current, voltage into current dimensionally becomes power. So IS is again how much? IS magnitude is 20 amperes. So it becomes this becomes 1200 watts, this becomes 1600 VAR, and this becomes 2000 VA. Is it okay? We generally represent this complex power by S. This is complex power. So what is S? It is P plus JQ. The complex power is P plus JQ. This is a phasor. So S is usually when we represent active power by P and reactive power by Q, there we represent the apparent power by S. What is this, by the way? It is Vs magnitude into Is magnitude. So 100 into 20 is 2000 and it is volt amperes. Dimensionally these three powers are the same. They are simply voltage multiplied by current, but just to differentiate, we express one in watts, another in VAR, and the resultant in volt amperes. Again, this angle does not change because this is theta S. Is this okay? So we call this as the impedance angle. This is impedance angle. This is our triangle, we must call it a triangle, impedance triangle. This is voltage triangle, and this is what we call as the power triangle. This is called as the power triangle. Is this okay? So this is how for this one particular circuit we can do these many calculations. Is this okay? So these are called as complex calculations. So we have seen that how can we calculate the voltage phasors, current phasors, represent them on the diagram. The basic fundamentals have to be always followed. For an inductor, the current will lag with respect to voltage by 90 degree. For a capacitor, the current will lead the capacitor voltage by 90 degree. For a resistance, the resistance voltage, that is the voltage across the resistance and the current flowing through it, will always be in phase. Why do we take this conjugate? This is only to follow the rules of reactive power flow. An inductor must absorb power, so it has to be positive. A capacitor must supply power, reactive power. When I'm saying power, I mean to say reactive power. An inductor absorbs reactive power, a capacitor supplies reactive power. So for an inductor, it has to be taken positive. For a capacitor, it has to be taken as negative. So I have to make this negative into positive, and if it was a capacitor, that positive would have to be made into a negative. So that's why this asterisk or this conjugate has to be taken for the calculation of complex power. So we can represent all the phasors on the phasor diagram and the quantities in the form of a triangle, giving them the different names: the impedance triangle, voltage triangle, and power